Every system has associated with it a quantity we call the total energy, symbolized by capital E. Logically enough, the total energy is the sum of all the energies in the system. We see over here mentally, and this is just a cartoon, we have a system boundary, system enclosing some stuff. Inside of it there are many different types of energy, and the total energy is just their sum. We haven't shown it yet, but energy is a scalar. All the types of energy are scalars, so this is a simple arithmetic sum. You don't have any weird tip to tail stuff or any kind of dimensional stuff going on. You can just add them like numbers. There are many forms of energy connected to the various kinds of forces in the universe. There's some things that call kinetic energy and potential energy, thermal energy and nuclear energy, and so on. We'll be developing each of these over the next few sections, but following is sort of a quick list of the major types. So, just like with forces, we're going to now develop the big book of energies, a list of the type of energies you might run into. Kinetic energy, symbolized by capital K, or sometimes as just the straight letters KE, is the energy of motion. Anything that's moving has kinetic energy. There's a root kind of hint in that because kinesis, remember, is the Greek for movement. Kinetic energy depends on the mass and the speed of an object. If two objects have the same mass, the faster one carries more kinetic energy. And two objects have the same speed, the more massive one has more kinetic energy. Think about this. Remember that energy is the coin you pay to make things happen. A car moving faster can do more damage. It can make more changes in the universe than a thing moving slower, at least in a collision. Notice kinetic energy does not care about direction. A car that's moving 10 meters per second northward has the same kinetic energy as a car boosted into the air at 10 meters per second. The other great type of energy is called potential energy. Potential energy, which is symbolized by capital U, or sometimes as just PE, is the energy of arrangement. It depends on how the objects are positioned relative to each other. Often people describe potential energy as energy stored in the system. Potential energy comes in many forms. The two that we'll spend the most time talking about are gravitational potential energy, U sub G or PE or GPE, gravitational potential energy. This is associated with the separation of gravitating objects. Usually the height of something is above the ground. It increases with increased separation, or with height. All right, so the higher if I have two objects that are otherwise identical, but one is higher off the ground, then it will have more gravitational potential energy. There's also what's called elastic potential energy, U sub S or EPE. You might wonder why the S. Because it's associated with springs or other elastic objects. So this is usually the energy of a spring. The greater the deformation of the spring, the greater the elastic potential energy stored in it. So if we take two objects on two identical springs, but we stretch one spring longer, it will store more energy. Thermal energy. Thermal energy, which is symbolized by E sub th, little th, or, usually E sub th, is the energy associated with temperature. Hot objects have more thermal energy than cold objects. Often we'll consider the thermal energy to be essentially constant and we'll neglect it. So they'll be very explicit about whether the thermal energy in something can change or not. On the atomic level, thermal energy reflects the random motion of atoms and molecules. And so it is, in a very real sense, just kinetic energy. But it's kinetic energy that we can't track directly because keeping track of quintillions of atoms is not practical. In our money analogy, this is sort of like change, like pennies and stuff that you've dropped behind the counter or under your couch or whatever. They still exist, they're still money, but they're hard to track. They're hard to keep track of. They're not useful. Likewise, thermal energy is hard to use usefully. It's often described as waste, which is unfair, but it's not organized, and so it can't easily be turned into work, which is the thing we'll be talking about next. There's also chemical energy, often symbolized by E sub chem. This is energy associated with the chemical bonds between atoms in molecules. Bonds can be broken, quote unquote, because really there's no physical object being broken, but we can make the bond not there. And that energy can be made available as heat or kinetic energy. Likewise, kinetic energy or heat could be turned into chemical energy and stored in bonds, making new bonds. This is the process that goes on, for instance, in making ATP in cells and then breaking them down later to get energy back. Nuclear energy, symbolized by E sub nuc, is similarly the energy associated with the bonds among subatomic particles. So instead of between atoms, between the parts that make up atoms. Since chemical and nuclear energy result from the arrangement of atoms or subatomic particles, they are really potential energies. And in fact, basically all energies will fall down to being at root either a kinetic energy or a potential energy. And we usually reserve the terms kinetic or potential energy for organized and macroscopic things. Of course, it'd be pretty boring if all forms of the energy remain constant all the time. Just like it'd be a boring world if everyone always had the same money they started with. If you couldn't spend money, then it wouldn't matter if you had it. Human economy happens when money changes from one account to another. Physics happens when energy transforms from one type to another. For example, a roller coaster car at the top of a track. So let's say here's our roller coaster. That's pretty bad. And we start a cart up here. It might have gravitational potential energy because it's some height above the ground. And then it turns into kinetic energy as it moves along. All right? Likewise, gasoline contains a large amount of chemical energy, which the engine turns into heat and eventually into kinetic energy of the car. So, what energy transformation occurs when a weightlifter raises a barbell from the floor to a resting position above her head, as shown? The barbell is higher, so its gravitational energy has increased. It began at rest, so there was no kinetic energy then. The cells in her muscle converted their chemical energy into kinetic energy and then into potential energy. Notice that at the end, when it's resting, there's no kinetic energy there either. So it has turned all of that chemical energy has now eventually been turned into potential energy. To be honest, probably some of it's been turned into heat as well. What energy transformation occurs when a base runner slides into the base? Well, the base runner starts off moving, so he has kinetic energy K. But his height does not change, therefore neither does his U sub G. The dirt and his uniform, however, both get somewhat warmer as the kinetic energy is converted into thermal energy. Right? At the end, of course, the base runner has stopped after the slide, so there's no more kinetic energy. It's all been turned basically into thermal energy. What energy transformation occurs when a springboard launches a diver to his maximum height? Well, the deformation of the springboard gave us some energy stored there. This is elastic energy because it comes from the fact that the board is disturbed from its original shape. When it relaxes, that energy is turned into gravitational kinetic energy of the diver, but at the maximum height, all of the kinetic energy has been gone too. So all of that EPE has been turned into GPE.